Okay, today we're going to find linear approximations. Okay, so what we're going to do is we're going to take some notes and then you will work on homework. In that order, right, Harris? Okay. So, 5.5, I can find the linearization. Let's jump in. Linearization, technically, index card wise, it's L of x, we notate it. A/B test, we use the same notation. F of A plus F prime of A times x minus A. It's called linearization. But that is not new. So let's think about what this is. If I have a point A, my y would be F of A. If I did a tangent line and point slope forward, I would have y minus your y value. Your slope, which is the derivative, evaluated at A, x minus your x value. Solve for y, add that to the other side. Y, L of x. This is just a tangent line. That's all this is. It's just a tangent line. They say a fancy word, linearization, for a tangent line. Okay, so let's try one. Find the linearization of f of x at x equals 0 and use it to approximate 1.02. So let's first ignore the second part of the question. Let's focus on finding the linearization. To find the linearization, I need the point and the slope. It's just an equation. Let's go ahead and find our x, y real quick. Our x is 0. Plug in 0. My y value is 1. Now I need the slope, so let's find the derivative. F equals quantity 1 plus x to the 1/2. Chain rule. Do a little cheat here. Like I said, unless you start messing up, I'll let you do this. Derivative of the inside is 1. So I get for my derivative 1 over 2 square root 1 plus x. So now plug in your x value, which is 0. I will get 1/2. There's my slope. So let's do a tangent line. So y minus 1 equals your slope, x minus your x. Now I'm going to go ahead and replace my y with L of x, because it is a function of x. I get 1/2 x plus 1. There's my linearization. It's just a tangent line and we replace y with L of x. Okay, so now I have to use it to approximate that. So, compare this with your function. What would x had to have been, what would it have to be in order to get 1.02 in the inside? So if that's 1, x would have had to have been 0.02. Follow me there? So now what we're going to do is we're going to plug it in here. So L of 0.02, I'm going to convert to decimals. You can multiply that out. That'll give you 10 with 3 decimals. Right? 5 times 2, 1, 2, 3. So it'll give me 0.01 plus 1, which is 1.01. So we're saying the decimal approximation of 1.01 square root is 1.01. So let's look at our calculators and let's check it. Second square root, 1.02. Control enter. Yeah, that's about 1.01. Pretty close. Now, key to note that we use an x value for our linearization as 0.02 with a linearization at x is 0. These have to be fairly close in order for my approximation to be close. So if I were plugging in x equals 5, that's not going to give me a good approximation of that square root. Okay? We have to be very, very close. Okay, so now you have a you try. What I ask is that someone please pause the video right now while everyone works it, and then when everyone seems to be done, so pause for a couple minutes, then go ahead and push play when everyone seems to be done. Okay, hopefully everyone tried it. Obviously you can't click in. So let's go ahead and find our y value. So pi over 2, plug it into our function. Cosine of pi over 2 is 0. My derivative is negative sine x. So plug in pi over 2. Pi over 2 here is 1, but you have a negative. So there's my slope. So my equation is y minus 0 equals your slope, x minus pi over 2. So I have y equals negative x plus pi over 2. Oh, let me go ahead and replace it with L of x using correct notation. Okay, so there's my linearization. Now we're going to use it to approximate cosine of 1.75. So compare this and this. X would have had to have been 1.75 for those to be the same statement. So I have L of 1.75 equals, plug it in, negative 1.75 plus pi over 2. Now the whole point is to get this without a calculator, because I could easily type in cosine of 1.75 on my calculator and know what it is. The whole point is to do this without a calculator. This is how math was done pre-graphing calculators. Okay? So we should know the decimal approximation for this. I know some of you may not know it right now. If you don't, you can easily find it. 3.14 divided by 2. And we want 3 decimals. Okay, they might give 2 in this case. 3.14159. So 2 goes into that once. Bring down. Goes into that 5 times. Bring down 7. Bring down 0. So it ends up being 0 there. So we're going to use 1.57. It is 1.570. So negative 1.75 plus 1.57. Signs are different, so you're really subtracting them, knowing it's going to be a negative number. Negative 0.18. Okay, now let's check. Let's check our calculators. I want cosine. Whoa, okay. Go away. There's my ghost showing up again. Cosine of 1.75. If it will type in. Let me go to my computer. So we're fairly close. We have negative 0.18 if we round it. So the whole idea of a linear approximation is without a calculator to find tricky values that we may not know. Okay? So without a calculator, back in the day, to find cosine of 1.75, you may not know that. In fact, you didn't know that without a calculator. You need a calculator to find that value. So what a linearization does is it gives us an estimate without a calculator, without the use of technology. So this is almost always on the no calculator part of the AP test. Okay, so now we've got linearization. Let's do a word problem. This is how they often show up on the AP test, is a table. They usually don't say find the linearization, although they have before. I've actually seen it on extended response. But usually it's a table. So we have a sensor that measures the position of a particle t microseconds after collision. Estimate the position of the particle at times t equals 8 and t equals 12. Okay, people who don't study do this. Part A. Well, 8's in between 5 and 10, so I'm going to pick a number 11. That's closer, 10, 12. You can't just pick a number. You can't make up a function's value. That's actually what we're going to do is find linearization to find function values. So I'm going to find linearization at t equals 8. And then, once I have that line, plug in 8. So 8 is in between here, so I'm using these 2 points. Now, 8 is closer to which one? Well, is it closer to 5 or closer to 10? Closer to 10, so we're going to use that as my point. 10, 14. Now I need to find the slope, which is your y minus y, x minus x. So I have 14 minus 8, 10 minus 5. So that would give me 6 fifths. So I have y minus 14 equals 6 fifths. use L of x. Okay, so let me add opposite, distribute. So I'm going to go ahead and replace it with L of x equals 6/5 x minus, times those, these will reduce, you get negative 12, right? 2, 6, negative 12, plus 14, plus 2. Hopefully that's correct. So 5, 2, yeah. Okay. So now you're going to plug in 8. So here's my linearization. Now plug in 8. L of 8 is, I'm going to go ahead and plug that in. 6/5 times 8 plus 2. Okay, we can do our calculations here. I can't use without a calculator, I can't use without. But we end up getting 58/5, which is approximately, let's see, 11.6. I just use the calculator for the simple math just for time's sake. But of course we know how to find common denominators if this were an AP no calculator question. So now look at our table. Does 11.6 sound reasonable? Is that in between 8 and 14? Yeah, sounds pretty reasonable to me. Now if I were to do part B, t equals 12, I have to start all over. Because t equals 12 is in between two different points. T equals 12 is in between these two. Now 12 is still closest to 10, so I'm still going to use that as my point, but my slope is different. Y minus y, x minus x. So 18 minus 14, 15 minus 10, 4/5. Okay, so y minus 14 equals 4/5, x minus 10. So I'm going to go ahead and change to L of x. 4/5 x, let's see, that give me minus 8 plus 14, so plus 6, I believe. Let me check it. Times 2 be minus 8 plus 14. Yep. Okay, now that we have linearization, let's plug in 12. Like I said, I know you can use some little common denominator here. It's not a lot of work, but I'm going to go ahead for time's sake and plug in. 78/5, which is approximately 15.6. Is that in between your two values? It is. So it looks deceptively small. It's a small problem, but it does take a lot of work. Alright. Let's try Newton's method. Newton's method is actually a very easy method. It just gets messy on a calculator. It's used to approximate the zeros of functions. So once again, this is something you can do without a calculator. Your zero command on the calculator, that's what it's using. Okay, so when you actually use that zero command on a graph, it's doing Newton's method. Okay, so what Newton's method? You first make a first guess using a graph. So it looks like, it looks like it goes through 0.2. Just general, maybe 1 decimal, nothing extravagant. Okay. Then you use that first approximation to get a second, and use the second to get a third, and the third to get a fourth by using this. Remember, this is sequence notation. It's saying if x sub 1, 1 is your counter, then you can plug it into your function divided by your derivative, and that should give you the next one, x sub 2. Likewise, x sub 3 would be x sub 2 minus f of x sub 2 over f prime of x sub 2. You're just getting the next one. Alright. So let's try one. We're going to use Newton's method to estimate the zeros. And when we say zeros, we mean all of them. So if it crosses more than once, which you have a few in homework that do, you have to use Newton's method on each one. Okay. So I need the derivative. F prime is 9x squared plus 2x minus 3. Now we need a first guess. Okay, so let's graph this in our calculators. So go to a graph. should be doing this with me. If you aren't already, you better be grabbing your inspires. Minus 3x minus 2. Okay, you can zoom in if you'd like. We don't need to, we just need a generic guess. Looks like it crosses at 1. You can say 1.1 if you want to be accurate, but usually we do 1 decimal or whole numbers, whichever is closest. So my first guess I'm going to say is 1. So let's write that down. That my x sub 1 is 1. Now I need to find my x sub 2, and to find that, I use my x sub 1 plus the function evaluated at 1 divided by the derivative evaluated at 1. So I'm just using, just using this formula right here. Okay, that's all I'm doing. Oops. My computer will cooperate. Now, we could easily plug that in, but this gets pretty nasty with our calculators. We don't want to do this each step because we need to go 4 or 5 steps usually. So we need to figure out some shortcuts with our calculator. So I'm going to show you a couple different ways. There are tons of different ways to do this on your calculator. One is a long process, is to store your first guess. So I'm going to go back to a scratch pad calculator. Okay. I'm going to type in 1 and I'm going to control variable, store it into D. Doesn't really matter what variable. I tend to stay away from X. Then I'm going to type in my expression, which is D minus, open your fraction, F of, so that was 3D cubed, I think plus D squared, like that. I'll look it up in a second. Plus minus 3D minus 2. Over the derivative, which was 9d squared plus 2d minus 3. Control Enter. There's my second guess, 1.125. Once again, you should be doing this with me. So 1.125, and never ever ever round. If it gives you 9 decimals, you write down 9 decimals. Do not round. We're trying to be as accurate as possible with Newton's method. Alright, so now I need a second one. Well, the easiest way why I stored it is to just take my answer. I'm using my up arrow. Enter. Control, store it into D again. So I'm storing my new answer. Now use your arrows. Go up and grab that expression. Control, enter. There's my second guess. Okay, so trying to remember this to write down is going to be interesting. Where I need you guys right here with the calculators. So x of 3, approximately 1.097. Oh, 1097. Let me fix that real quick. 1097. 650514. 650514. So now let's find the fourth one. To do that, go up, grab your previous answer. My calculator will work here. Grab it, store it into D. Go back up, grab your expression, Control Enter. Okay, so 1.1095. Keep going. So go back, take your answer. Enter. Control, store into D. Go back, grab your expression. pretty close, except my last one is a 1092. You may be thinking, how far do we go? Well, we keep going until there's no change in that decimal. So let's see, that should be enough. Usually 4 or 5 steps is enough. Well, let's go check it out. And voila, there's no change. Okay. So my answer is this. That is my 0. Okay. Now, obviously, that stinks. It takes forever. There are other ways to do this. You can do a table with some copying and pasting. That does it as well, but you kind of have to watch your decimal values of how many you get because you want all of them. Sometimes the table will round that for you. But this is not an ideal way. Okay? That is one of the quicker ways, but still is very long. So we do have a program that I gave you last week. Now, if you don't have that program, if you weren't here or you forgot your calculator that day, make sure you come see me tomorrow morning to get it. I was hoping you would come see me. I told a few of you or one of you to come see me before then, but I haven't seen you. Okay, so let's use a program. Let me clear this out because I don't like junk in there. Okay, so go to your documents. We're going to File, Open Document. Okay, I'm going to use my computer. You're going to scroll through. I think I put mine in Calculus AB. You might have some subfolders in there. You will see Newton's method. You should see Newton's method somewhere in there. I want everyone to be opening this. It asks me if I want to save what I have open. No. Okay, when you open it, I kind of cleared out a bunch of stuff you don't need. The first one is just giving you some directions, the first page, and it has Newton's formula on here, in case you've forgotten it. Shame on you. Which of course you will not be given on a test. But it says the first step you're going to do is you're going to define the function by graphing it. Then you're going to edit the text to set your initial x naught. You've got to set your first guess. They use x sub 0, which is x naught. So I want to go to the next page. Okay, you can either tap it with your arrow, or you can do Control, next page, move over. Okay, either way. Now, what you'll see is there's already a function there. It doesn't like you to leave it blank, so I just put in y equals x. So make sure you're on this screen. If right now, see how this is kind of bolded? I won't be able to control that. So I need to go over. I'm just going to try to use my arrow. And tap on this screen. It doesn't like it from my computer. So I'm going to use my computer, you do that. But now, use your up arrows. Do not delete what's in f sub 2. Do not delete that. That is used for the program. But go to f sub 1. This is where we would enter our function, which was 3x to the third plus x squared minus 3x minus 2. Go check that real quick. Yep. Hit enter. It's going to graph that, which we need the graph anyway to get an estimate. So looking over here, we still say our first estimate is 1. So right down here, use your arrows to go to this box. Or use your mouse that you've got. I'm going to use my mouse. It doesn't read it from the board. I'm going to say my first guess is 1. I'm going to find x naught is 1. I'm going to say in step 1, hit your arrow in this box. Saying when they use, let me emphasize this real quick. I went straight to 1, 2, 3, 4, 5. They use 0, 1, 2, 3, 4, 5. It does not matter what you do. At all. Does not matter one way or the other. So they said their first guess gives you 1.13. We would write that down. Then hit your arrow again. Their second guess gives you this. Third guess, it'll read that. I might use my computer. Third guess gives you that. The fourth. Until you see there's no change. Now, it's not as great as the scratch pad screen because it does round a little more. It's not perfect, but it's enough to get us by. So this is sufficient. We do have a good amount of decimals there. Let's see, how many do we have? 9 decimals, which is okay. Now, what I would do before you accidentally make any changes to your program that you can't undo is I would close your program out. And you can document to a file. You can say, I wouldn't save any changes. Just put new document, ask you if you want to save the change before you exit. I would hit no. You don't want to really change your program values. So let's try another one. Well, I'll let you try your program on the U-Try. So try your program. Make sure you write down all of your guesses. So what I need to see for your homework is X0 is approximately, X1 is approximately, X2 is approximately, X3 is approximately, X4, however many you need until it doesn't change. I also need to see that you found the derivative. That is enough work for me, and then circle your answers. But I want you to use your program. Try to find Newton's, try to find all the zeros using Newton's method. Okay, so somebody pause the video and hit play when everyone seems to be done. Okay, let's try the program. So hopefully somebody paused the video and you're now replaying it. I'm going to Documents, open my document, open up Newton's method, go to the second page, make sure I'm on the graph screen, scroll up to F1, delete what's in there. I think I have x to the third, let's see, plus 3x plus 1, enter. Looks like my first guess I'm going to say is negative 0.5. Negative 0.5. So that's what I said as my first guess, so I would write that down. Then use your arrow. There's my second guess, or x of 1. There's the third one. Fourth, fifth, and it looks like it stopped changing there. So that would be my answer that I would write down. Negative 0.322 or 0.322185355. Boom, done. Okay, so obviously the program is the easiest way to do this, and yes, you are allowed to use programs on the AP test. So that is the easiest way to do that one. Alright, so homework 2.9 is 5.5, 1 through 6, 53 through 56. I want to emphasize that these are Newton's method, right here. Now, if you have a function that hits twice, two things. If it's symmetrical, please only find one, and then just use plus or minus your answer so you're not doing extra work. But if it's not symmetrical, you have to use Newton's method on this, and on this. So there would be 3 different answers there, and 3 different sets of your guesses. Now 1 through 6 has some funny language, so let me open that up real quick, because I have a lot of people come in the next day and saying they were confused about the language on that. So let me open up the book, and right now all of you open up your book because I want you to see it as well. So everybody should be opening up their books. Okay, 1 through 6, the directions are kind of confusing. Okay, so part A says find a linearization at x equals a. That's pretty straightforward. Do your linearization at that point. That's your x. Okay, they just used a in this case. Okay, then B, how accurate is the approximation L of a plus 0.1 compared to F of a plus 0.1? So what you would do is you take your a, in this case 2, add 0.1, 2.1. You would plug in 2.1 to your function, plug in 2.1 to your linearization you found in part A, and compare them. Oh, it's an overestimate. It's an underestimate. You're off by 0.3. Okay? Something in your own words. You don't have to use the book's words. You use yours. Oh, I'm very close. I'm off by 0.01. Okay, that could be an explanation. So that's what part B is. So on like on number 2, -4 is your x. You'd add 0.1, so -3.9. You'd plug in -3.9 to your function, -3.9 to your linearization that you found in part A, and compare them. Okay, a lot of people think that language is kind of weird. Okay, so right now, obviously I will not be here for tutorials because I had to leave for a doctor's appointment. So I will be here tomorrow morning for tutorials. So if you have trouble on any of this, come see me. Or if you need the program, come see me. If you don't have the program, it's just looking over a friend right now. Okay, but definitely come see me. You might have to do the old-fashioned way for homework, unless you can catch me before school tomorrow and have plenty of time to do that. So homework time right now. Go ahead and work on 5.5. Tomorrow we're starting 5.6.